So this presentation is on mass spectroscopy. This is quite a different technique from UV-Vis, IR, and NMR. All three of those are based on the electromagnetic spectrum, whereas mass spectroscopy is based on a completely different technique of fragmenting molecules. Let's go on. What is exactly mass spectroscopy? It is a measurement of a mass to charge ratio of ions in gas phase. So what we do is you take a molecule and then you fragment it. So take an organic molecule, fragment it using electrons, and what you would end up getting is a cation and a radical. And the cations are what are detected by the mass spec, the radicals are not. And so those cations will then be detected. Okay, and that is the mass to charge ratio that is observed. And what mass spec does is it gives a very good idea of what the molecular weight or mass of a compound is. So it's a very good technique if you don't know anything about the molecule. In some cases, it is actually used to confirm a molecule. So for example, if you know what you're making, then you do a mass spec at the end to confirm the mass of it. Depending on the fragmentation, it can also give some information about the structure of the molecule, although that is a little bit hard because rearrangements happen and whatnot, and so this is a little bit harder to do, but at least you can tell the weight of any molecule. So this is what a mass spec looks like. Okay, here is the relative abundance. And the relative abundance on the y-axis, this one goes up to 100. And the 100 is based on the largest peak in the spectrum. So the computer by itself will pick up the largest peak, which is called the base peak, and then it will calculate the relative abundance according to the base peak of everything else in the molecule. So the base peak then is the most abundant peak, which in this case is 124. Then there is the molecular ion peak. The molecular ion peak is really what most organic chemists are looking for because that is the peak that has not fragmented. Okay, or that's the mass that's not fragmented, which means that it is the mass of the entire molecule. All the other pieces that you see here, these are all fragments of this molecule, which is dopamine, okay, in this case. So this one, the molecular ion peak, is not fragmented. This scale over here is M over Z, which is mass to charge. The charge is usually +1, so essentially this is mass of the ion. So this is what a mass spec looks like. It doesn't have peaks as such as in a curve. It actually just has straight lines like this, and a lot of these little lines, which we will talk about in a little bit. This is the instrument. One of the things that I should mention over here about the instrument itself and sample is that the sample that you use in here is actually all used up because once you put the sample in the mass spec, it fragments it, it vaporizes it, and it fragments it. So which means that at the end, you don't have any of your sample left. So your sample is destroyed. So you should be ready for that. So right here, you put your sample in, and what it does is it will vaporize your sample and then bombard it with an electron gun, which really essentially is electrons. And what that does, it actually fragments the molecule. And this over here is a magnet. This is almost like a racetrack, if you would. And all the fragments then start accelerating over here, kind of like a race. And obviously, the heaviest is the loser and the lightest is the winner, and the lightest fragment comes out first and is detected first. The largest molecule or the unfragmented or the largest fragment will come out at the end, and then that is detected. Usually the largest one or the last one to come out is the molecular ion peak. So that is the one we are looking for anyway. So we actually like the last peak in this one. In any case, mass spec is usually a huge instrument. If you want a really good mass spec, which means if you want weight up to 4 decimal places, then you would want a really good high resolution instrument. And those kind of instruments can be really big and expensive also. On the other hand, there are smaller mass specs which are, much smaller and a little bit more portable. Anyway, this is kind of how the mass spec works then, okay? So you have a sample intake over here, and then bombarding it and then accelerating it. And then of course the detector, which goes then to a computer where it analyzes the data. One of the things that you would have seen in the last slide, actually the one before that, is all the different little peaks that we had in there. And all those little different peaks actually correspond to isotopes. Almost all elements that we deal with in organic chemistry have isotopes. And so those isotopes will also show up in the mass spec, just like any element on the periodic table has isotopes. Um, these elements here that we study a lot in organic also has isotopes, of course. And so hydrogen, for example, has 3 isotopes, but 2 of them are more common. The third one doesn't have a very good half-life, and so you don't really see it so much. Relative abundance is how much they are completely. And then, of course, the second one, the second isotope here, which is H2 or heavy hydrogen or deuterium, is a very, very small percent of the original. Carbon here has 2 isotopes, 12, 13. Of course, it has more, but these 2 are the ones that are even small, are measurable. So the carbon 13 is only 1.11%, which is very less. Okay, and so carbon 12 is the most abundant isotope. So then we have isotopes for nitrogen, oxygen, sulfur, chlorine, and bromine. We will talk a lot more about the chlorine and bromine isotopes because look at the relative abundance, okay, for these isotopes. For chlorine, 35 to 37, the abundance is almost 3:1, okay, which means that the 37 isotope, which is the less abundant one, but it is still 1/3 of the entire mass, whereas in bromine, the 2 isotopes are almost in equal proportion. So that shows up really nicely in the mass spec, okay? So this is a very good way of telling if you have chlorine or a bromine in your sample, okay? But otherwise, the little small peaks that you see all the time in mass spec, these are going to be all the isotopes which all show up whether you like it or not. They're going to. So here is a little example for the chlorine peak, okay? So this compound here, which is just chloroethane, very simple molecule. Chloroethane has a mass of 64 and it's so high being a small molecule is because of chlorine, okay? So chlorine is 35 mass, and right here, okay, it's a very clear indication of the 1:3 ratio, okay, 1:3 ratio of the molecular ion peak, and that is because of chlorine. Once you get to 29, you don't see that anymore because 29 is the mass of the ethyl fragment, CH3CH2, so you don't see the chlorine in here, so you will not see the 1:3 ratio. But right here in the molecular ion peak, you will see actually 2 ion peaks, the M peak and the M+2 peak. And the 3:1 ratio tells you that you have chlorine in there. So it's a very clear indication of the halogen. Here, this one is for bromine. Now, bromine is a really heavy atom. 79 is the mass. So if you take something as simple as propyl bromide also, it's going to come out really heavy. But the key thing over here is, again, these molecular ion peaks, which are M+2 peaks, and they are equal in ratio. So as soon as you see 2 equal ratio peaks, that indicates that you actually have bromine in there. Once the bromine is gone, what is left then is the next peak, which is 43. So 43 is for the propyl cation, and this is the molecular ion. So 43 doesn't have any bromine in it. So all you see is the M+1 peak, little tiny peak there for carbon isotope, but otherwise not the 1:1 peaks, okay? And so this is the characteristic for bromine in a mass spec. What I would like you to note over here also as we are looking at this is that you have a propyl peak and you have the propyl bromide peak, okay? So this is the propyl bromide peak, and the base peak is the propyl ion, which is actually quite stable. So that's the base peak over here. And then 29 is the ethyl peak, okay, which is CH3CH2. There is hardly any methyl ion, okay, and we will talk about the fragmentation of alkanes, but you don't really see much of the 15 because it's not very stable, okay? 15 is carbon, which is 12 plus 3 for hydrogen, that's 15, okay? And so the base peak is actually propyl. So the fragmentation that happens for mass spec again is kind of like a fingerprint, which means that if you have a compound in the database, then you can take your mass spec and compare it to anything in the database, and it should have exactly the same fragmentation patterns. So it's almost as good as IR, okay, in its detection, or I should say comparison, okay, not so much as detection, but as comparison. So if you have a database of it, then it's really helpful to compare and then confirm, okay, of what you're talking about. Then the other thing I want to talk about here is, of course, the cations that are formed during the mass spec. And the cations will form on the basis of stability. And so the tertiary, which is allylic and benzylic kind of a cation, is very stable. And then the secondary allylic and the tertiary carbocation, secondary carbocation, and then the primary and the methyl cation. The methyl cation is the least stable, as you know from Organic 1 also. It's the same kind of a thing over here, okay? So there's nothing different. The more substituted the carbon is, the more resonance stabilized it is, the more stable it will be. So that's the cation that's going to form. So if you have neopentyl, then it will rearrange to give you, or it will fragment to give you this cation, which is the t-butyl cation, which means that you will not find the cation on the methyl. You will find it only on the tertiary carbon right there. So this is kind of what happens in fragmentation. So it's sometimes it gets a little bit easy to identify what the most abundant peak will be. So interpreting the mass spec, this is always a little bit tricky as far as looking at it for the first time. It might seem a lot of jargon to you, as if nothing is making sense, but hopefully as we go through the presentation, you will have a little bit of an idea of how to interpret mass spec. Remember, you're not going to become experts after listening to this presentation. You will just get a little bit of an idea of what you're looking for. Okay, so the first thing you have to see is what kind of peaks are present there. Okay, if you have an M+2 peak, then maybe you have chlorine and bromine. Look at the ratio of those peaks. 1:3 is for chlorine, 1:1 is for bromine. So if you see those two, those are your clear markers for chlorine and bromine in there. And then there's a nitrogen rule about odd and even. We don't usually deal so much with nitrogen compounds in mass spec. I will stick mostly to alkanes and maybe some alcohols. Okay, we don't do a whole lot of amines or amides in mass spec. Okay, so but here's a nitrogen rule also in case you're looking at something else. Okay, so here is our first mass spec. We are looking at octane. Okay, and this is a huge molecule, and I love this mass spec because it's such a huge molecule. You can actually see the small fragmentation going on, and this is something that you have to actually calculate. And so for mass spec, you will need a periodic table and maybe a calculator if you want to do this faster, all right? Because you need to add up the masses of carbons and hydrogens and any bromines or chlorines that might be in there. But there are some masses that you should just have on the tips of your fingers so you can add them up really quickly, okay? All right, in any case, this one is octane, and octane has a total mass of 114, which you can see over here, which is the molecular ion peak. Usually for any organic chemist, the first thing they do is you look for the last peak, okay, which is the molecular ion peak. It gives you the total mass. And then from there, you start calculating what the mass of the molecule will be. Okay, so in this case, our next fragment is 85, which is the total molecule minus ethyl group. Okay, and ethyl group is 29. That's the fragment. So the first fragment to go away is the ethyl group, which is 29, and that leaves us with 85. So you will see that there is also a fragment of 29 over here. And then you add 14 to that. So 29 plus 14 is 43. 43 plus 14, CH2, is 57. And then again, you add another CH2. So you keep adding the CH2s or remove CH2s if you're working your way backward. And then try to see what the different fragments are. The base peak here is for 43, which is a propyl cation, okay, C3H7, that's the base peak over here. And what that tells you is that propyl is the most abundant one in there. So, which means that if you take this molecule octane and you fragment it, you will get propyl twice, okay, because it's C8. So you get propyl ion twice, and if you get that twice already, it makes it a large amount of ions in there. And so therefore 43 becomes a nice big peak, which tells you one more thing though, that octane does not split just into half. Okay, so which means you don't get two butyl cations, you actually get two propyl cations. Okay, and that is just the way it fragments. It's not something that you can argue about or you can do anything about. This is just the way it fragments. Okay, and so there is no reason to go there and think about all those things. All right, so just look at the base peak and then figure out how many carbons you have in there. Here is another one for an alkane, and this is a highly substituted alkane. All right, this is 2,2,4-trimethylpentane. So obviously you can tell that the largest fragment is going to be a C4 fragment, okay, which is the t-butyl fragment. That's going to be the biggest one because now this one, it can fragment into two right here. Okay, so after the t-butyl over here, so you have 1, 2, 3, 4 carbons here, and then 1, 2, 3, 4 carbons here. So this one really will give you a 57 peak because this molecule will fragment directly into half to give very stable carbocation, a tertiary carbocation. So this is pretty stable. So 57 is your base peak. Here is our total peak, which is 114. Now, if you notice, this 2,2,4 trimethylpentane is a constitutional isomer of octane. Okay, so which means that we still have 8 carbons. All right, but look at the fragmentation patterns. They are so different. Okay, between the two. In that one, we had the propyl, which was the base peak, and now here we have the butyl, okay, which is the base peak. So, and this one is because of the way the molecule is arranged. All right, and so this constitutional isomer will give 57 as the base peak. You still have the 29, you still have the 43s and 47s, but excuse me, the 43, but this is the base peak. Okay. Here is another one, and this is methylcyclopentane. For cyclic compounds, the fragmentation is entirely different. Okay, now you would think that you might end up getting a C5 as a fragment, but if you get a C5 as a fragment, that means that you will get a methyl cation, and yet again methyl cation is not all that abundant in this one. It means that you don't have a C5 fragment. It's a very small amount. Okay, it's not that big because you do have a CH3, so there is some C5 present, but the majority of the fragmentation is from a C4 fragment, which is a butyl. Okay, and then of course you have the ethyl one, because if you have a total of 6 carbons and you have a fragment of C4, you must have a fragment of C2 as well. So right here is the fragment for C2, and then the 43 right here is a fragment for C3. Okay, and then the molecular ion peak is right here at 84. So here the most abundant peak is for C4, okay, or 4 carbons, not for 5 carbons. Then we come on to alkenes. The interesting thing about alkenes is that that you can actually stabilize them by resonance, okay, and so you can draw various structures, and depending on what kind of compound you start with, you can have different fragmentations, and whatever fragment is more resonance stabilized is the one that's going to be formed, which in this case is a propylene kind of a cation or allylic cation, where the mass is then 41. So this is the base peak. And then here is the mass peak, which is 56. You have to calculate these things properly because alkane will be very close to that. Alkane is only 2 hydrogens short, so that will be 58. So you really have to watch out for the difference between alkene and alkanes, okay, as far as the mass spec is concerned, because the mass is only 2 hydrogens apart. So it's very easy to make a mistake. So be Here's one for alkynes, and again for alkynes, they are resonance stabilized. Otherwise, there's nothing fancy about this spectrum. It's the normal kind. You have a lot more peaks because it is just forming a whole bunch of isomers. Okay, and so again, there's no one carbon fragment here. There's more of the C2 and then the C3. Okay, the base peak, if you see in this case, is very close to the molecular ion peak, okay? Because molecular ion peak is 68 and 67, which is M-1 peak, is the most abundant one because the cation that is formed is resonance stabilized, okay? And so this is the base peak as well as the molecular ion peak. Alcohols are very characteristic as far as mass spec is concerned because they usually end up giving a M-18 peak, which is caused by the loss of one molecule of water. So the mass peak that you will see will not be really 74 for like this one. This is butanol. So the molecular ion peak is really hard to see in alcohols. What you would see is the M-18 peak, okay, which is 56 in this case. And then, of course, then more fragmentations go on. Don't worry so much about the resonance structures that I have drawn over here for you and all the isomers and not isomers, all the resonance structures, okay? Don't worry about all of that. The main thing I want you to know is that for alcohols, you have the M-18 peak, okay? That's the key thing because that's the kind of questions that I will ask you. Try to do this problem on your own, or of course go through this if you are looking at a mass spec problem for the first time. But the problem reads that it has the mass spec of an alcohol, okay? And so if it's telling you that the M+ for alcohol is 88, then of course you should be looking for fragments that are 18 less, okay, for alcohols. And so that's how you would start the approach, okay, for it. And then of course, then look for how many carbons you will have. And that will give you an idea of at least how many carbon fragments you're looking at, okay, in this case. But this is a solved problem. So go through it, and then we will try and do some problems in class also, which will give you an idea of what kind of questions you can expect for mass spec. So really for mass spec, you should know how the mass spec works, which means based on fragmentation. Know about the fragmentation patterns a little bit. And what that really means is, what kind of bonds will break, like we just talked about alcohol, that you get the M-18 peak, and you also get the M+2 peak for bromines and all that. So those are the patterns that you want to look for. And then of course know about the base peak and the molecular ion peak. The molecular ion peak gives you the mass of the entire compound, and the base peak of course gives you the most stable fragment, okay, whether it's an ion or radical, but it'll give you the most stable fragment, and that also helps you figure out what the structure might be, okay. And then in some cases with small molecular masses, you should be able to predict some structure, okay, and fragmentation and vice versa. If I give you a mass spec, you should be able to give me some sort of a structure for it. If I give you a structure, you should be able to tell me what kind of fragments I should look for.